Hi everybody, this is Dr. Powers. I wanted to take a little time to go through the Module 4 Lab and kind of walk through it, and hopefully this will help you. We're looking at random variables, and we're going to be exploring them in Stat Powers and just kind of exploring some of these concepts. This first one is a guided problem. So we're going to be exploring this random variable regarding the cost of books. So I'll read through it. A university bookstore offers a chemistry textbook for $159 and a book supplement for $41. From past experience, they know that about 25% of the chemistry students just buy the textbook, 60% buy both the textbook and the supplement. Of course, that means that there's some that don't buy either. Questions that we have to answer: what proportion of students don't buy either book? Let Y be the revenue from a single student. Write out the probability distribution of Y and compute the expected revenue from a single chemistry student. And then find the standard deviation to describe the variability of the revenue from a single student. All of this is talking about the revenue of a single student. Basically, we're going to be building this distribution of this random variable, and this will answer all of our questions. So the custom discrete tool allows you to build a discrete random variable, and here we have really the three possibilities for they're either like how much revenue they get from a student is either going to be 0 if they don't buy anything, right? It's going to be 159 if they buy the textbook, and it's going to be 159 plus 41. I actually built it so that if you put plus in here, it will add it together for you. But we actually don't have a third value, so I'm going to remove that. We only have those three amounts of revenue that are possible. It says 25% of the students buy just the textbook, so I'm going to put the 0.25 in here. And then it says 60% buy both, so put 0.60 in here. Now this tool will take the difference, and that is 0.15. You could do that yourself just using just a little bit of subtraction. So what we have here now is the probability mass function. These are the three values of this random variable, the random revenue. We have the probability of that somebody does not buy a textbook, which is 0.15. That was the first question we were asked. We have, so for part B, this is the probability distribution of Y, the random revenue. So you could write that out in a table. The expected value is actually the statistics, or I should say characteristics of this random variable are given down below. The expected value is calculated for us at 159.75. So that's it. This is to say, on average, the average revenue of students is $159.75 per student who takes chemistry. It's a weighted average of revenue, right? And then the standard deviation is also calculated, and the formula for it is a little bit ugly looking, but you could calculate it yourself just by hand if you wanted to, but it's a little bit. You got square roots and squares and stuff like that in it, but it's not going to be too many numbers since there's only three values that the random variable can take. But that's it. This is how you can build it. Now, we didn't do anything else with this random variable, but in some of the other problems we will do more. So we're considering a true-false test with 8 questions. If a student guesses at each question, the number of correct answers on the test will be a binomial random number. The number of Bernoulli trials is 8, and the probability of getting a correct answer is 1/2, true or false. And so we're going to model this using a binomial distribution, and I'm going to set the parameters n equals 8. Probability of correct is 0.5, so that's already the default value. So we can answer some questions. What's the probability that the student guesses 6 correct? To answer that, we can look for the probability equals and then 6. That's represented in that bar. This is calculated to be 0.1094, about 11%. All right, so that's fine. To simulate 5 students taking the exam, you can sample from this distribution. There's a sampling here. So we want to set the sample size to 5, which actually is the default value, and have a single one sample of size 5. I'm going to sample it, and so these are my 5 numbers that have been drawn from this distribution: a 6, a 7, a 5, a 4, a 2. So we can calculate some descriptive statistics from that if we wanted to. If you wanted to have a quick access to get the numbers, you can actually set the sample size to 1 and put 5 samples. It's going to just have 5 rows, and it's going to have the quote unquote the mean of each one is going to be just that number. And if you click Analyze, it will just bring the data into a quantitative analysis window, which you can look at like a histogram or whatever you want to do. Okay. So let's just look at what it would look like if you simulated 1,000 students taking the exam. I'm going to just actually set 1,000 here and click Analyze. Oops, I'm sorry, I didn't even sample. Sample, and I get 1,000 numbers. Click Analyze. That's my data. And let's see. We could, for example, look at the histogram. I always like to look at a histogram first because it gives a good picture. Now, here, because the data is discrete, the histogram would be better looking if I used discrete bars like that. That's a nicer way to depict this data distribution. Yeah. So if you wanted to ask questions about the proportion within this sample, you can actually use some proportion estimation. Like you can say, like, what proportion of students got, like, say, 6 or 6, got 6 correct. Well, say consider a success x equal to 6, and this calculates a sample proportion for you right here, and that is my estimate. Now, if you recall before, my probability was 0.1094. This is an example of what we call the law of large numbers, that a large sample from a random variable, a proportion is going to be close to the theoretical probability, and the larger the sample, the better. For this next one, Bernoulli-based distributions, this is the one doom game. In this game, you keep rolling a die, adding up your points on each roll until you decide to bank your points. If you roll a 1, then your accumulated points are wiped away and you pass the die to the next player. First player to 100 wins. So we're going to start the analysis by modeling the roll of a single die. So let's go to a custom discrete distribution. Modeling this is, well, we can... let's see, we're going to have 6 numbers, and click auto increment to, oh, nope, I started at 1. The tool auto increment, if I start the first value at 1 and then click auto increment, it's going to have the next one be 1 higher than that first. Auto increment is all based on the first value you put in here. Now these are all going to be equally likely probabilities. So let's see. The easiest way is actually, well, let's see. So if I put enter frequencies, it's probably going to be easier. Oh, you know what? The thing is, 0 was the right value. If I put in frequencies of 1 for each of these, stat powers will convert those into probabilities and round them off. I could have typed in 0.1667. Now it's going to bring that down to 0.1665 in order for them to all add up to 1. That's okay. It's not going to mess up our probability as much. In this case, so what do we actually, the expected value 3.3328. I mean, if I had more decimal precision, I'd probably, those 0.1667, I could have those go out to more decimal places. But this is fine. It rounds to 1.33 or 3.333, which is fine. So simulate rolling the die to see how long of a streak we should expect to get. For rolls of the dice, we can actually use this population that has been already built. I'm going to let's see. Let's bring that over to this window. So we have the die roll here. We're going to go to the. So let's sample and see what it looks like. Not a 1 and a 1. So that's all it is. It's simply not ones and ones. Under the sampling panel, get to this. We're going to set the sample size of 1,000. We're going to sample. We're going to analyze the die roll as a time series because we're going to look at streaks. And let's see. So this well, we're going to look down under streak analysis. The streaks. We're looking at streaks of not ones. 1, 2, 4, 3, 0, 0. Okay. So this is how long of a streak we had. So if you want to look, the first one is 1 not 1 in a row, and then there was a 1 that ended that streak. Then there was a streak of length 2, and then there was a 1 that ended that streak. Then 4 that ended. 3 that ended. There was a 0 streak between those two ones. A 0 streak between those two ones. Yeah? So 0 streaks do happen. We're going to analyze this as quantitative data. Let's look at the histogram. That's what the streak length looks like. They're actually discrete, so let's look at it in discrete bars. This is what you should expect when you're rolling a die, the streak length for 6. The number of rolls it takes until you roll a 1 is modeled by this. It's actually a geometric distribution. We could model it theoretically. So let's see. Suppose we take our turn. We decide that we're going to stop after X rolls and bank our points. What's the expected score per turn for playing strategy X? So we're going to go through these and kind of model these probabilities. We're going to look at the strategy, the simplest strategy, X equals 1. We already know that the expected value of this roll is 3.333. We know that. So let's think of it a different way. What's the expected value if we don't roll a 1? If we don't roll a 1, we could get a 2, a 3, a 4, a 5, or a 6 with equal probabilities. The expected value would be the simple average of these 5 outcomes. It would come out to be 4. So when we roll, if we don't roll a 1, the expected score is 4. The probability we don't roll a 1 is 5/6. So this is what we're going to be doing in each row of this table. And so the idea would be, what's the probability that we have no 1s after 2 rolls? It's going to be 5/6 times 5/6, right? And that's going to be, so that's 5/6. Well, that's going to have to calculate that separately. I'm going to actually do it in Google because it's the fastest way. 5/6 squared. 0.69444. That's what we're going to be doing down the line. The probability we get 3 non-1s in a row is going to be 5/6 to the third power, 0.5787. Then we can go down the line. That's going to be 5/6 to the fourth power, 0.48, 0.48225. Okay. Now, what's the expected score if you have no 1s? If you have no 1s, that's going to be 4 on the first roll, 4 on the second one. It's going to be 8. The expected score if you get no 1s after 3 rolls, it's going to be 4 on the first, 4 on the second, 4 on the third. It's going to be 12. That's how this expected score if there's no 1s. So this is the probability of no 1s times the average score you'd get. The expected score is going to be the product of those two. So I'm going to take 8 times 444. That gives us an expected score of 5.55552. That's the way we're going to go through this. 12 times 0.5787, 6.9444 expected score. 16 times 0.48225, 7.716. So that's the way you continue to fill this table out. you'll start to see the expected score will peak and then it will start dropping. That indicates that if you push your luck beyond a certain number of dice, you start to get diminishing. The risk of losing your points outweighs the benefit you might get from rolling and getting more points. So at a certain point, rolling a certain number of times gives you the highest expected score. And really, it would be better to think of this in terms of you, on your turn, you can choose to roll 1, 2, 3, 4, 5, up to 10 dice. You roll, and your score is how it's scored. So I think that's basically the idea for this. And honestly, maybe I'll rewrite this lab problem a little bit to change the game.